Welcome to Technical University of Denmark, the Department of Wind and Energy Systems. We are standing here in the large-scale facility. This is a facility where we can test large structures. My name is Kim Branner. I'm head of the section called Structural Design and Testing. And we work here with wind turbine blades mainly. We can do design, we can do manufacturing, and we can test these structures. We are in a climate crisis, and wind energy is one of the main solutions for the green transition needed for the world. A report showed a few years ago that offshore wind will be the backbone of the future energy system and can cover all the needs we have for electricity. Another trend is that there will be much more use of electricity in the future, because in industry, a lot of the places where fossil fuels are used now will use electricity in the future. And also in the transport sector, ships and planes will in the future run on green fuel, and these green fuels will be made from electricity, for instance wind energy, what we call power to X. So a lot of our research deals with design, manufacturing, and testing of wind turbine blades. So in order to really be better of doing and manufacturing, designing turbine blades, we need to understand how they behave. So a lot of research is about understanding the behavior of wind turbine blades, but also how they fail. How will they break when they are loaded to extreme loads? And in order to really understand these things, we need measurements. We need very precise, very good measurements, and that's where we use the ZEISS equipment. One of our flagship projects is ReliableAid. It's a project where we develop digital twins of wind turbine blades. And it started with a vision that in the future wind turbine blades will not just be the physical blades, but they also will come with a digital twin of each of the individual blades. And blades are different. So part of the project is that we have worked with scanning blades in order to figure out what the actual geometry are of the blades. And that's important because each blade are individual. And so that's included in the digital twin. Also, we want to understand how the blades behave during its lifetime. Damage will evolve in the blades, so it's important to detect these damages and update the digital twin so it always represents the true state of the blade, which can be used for many things important for the industry, for instance, to determine when to repair and maintain wind turbine blades. This project, ReliableAid, was fortunate to get an award in February this year, and we got a DIC Innovation Award. It's by some named the Oscar of the composite industry.
My name is Peter Bering. I'm a senior development engineer, and I've been here at DTU Wind and Energy Systems for 17 years. TriTop is an easy system to use. The system consists of a handheld digital camera and some calibration objects, which is known by the system. The measuring objects, in our case wind turbine blades, are equipped with coded and uncoded measuring points. By taking pictures around the measuring object, a 3D point cloud is created. The system can be applied both for undeformed and deformed blades, and the 3D coordinates can easily be analyzed within the system. An additional advantage of using TriTop for experimental blade research is that you get a strong digital documentation of your entire setup, which is captured by pictures from different angles. We often place points or markers on strain gauges, accelerometers or load cells. This enables us to map those locations onto numerical models or determine load directions. This is very handy for validation purposes, or if you want to go back and investigate how a test was performed, because that's captured within the pictures. Furthermore, TriTop is used as an extension of our ARAMIS measurements. When you need to measure a quite complex surface such as wind turbine blades, TriTop is used to create a 3D point cloud on the surface of the blade and the surrounding test setup. This enables bringing, for example, multiple ARAMIS measurements along the span of the blade into the same reference coordinate system. Hereby, you create a one-to-one comparison basis with a response computed by our high-fidelity models. This technique was utilized in the project called ReliableAid to create a strong validation basis for DTU's different numerical models. TriTop is an essential part of the large-scale calibration we use here in our lab. So at this very big scale typical calibration, objects such as calibration crosses cannot be used in a typical way. Here TriTop is used to create a volume which is known by the ARAMIS system, and therefore an essential part of the calibration. This technique we have demonstrated in our lab, and we are currently using this technique at the test center placed in Aalborg, Denmark, where multiple ARAMIS systems using this large-scale calibration is used on a 77-meter blade tested dynamically. So TriTop combined with our other measuring tools is a very important part of experimental blade research here at DTU. It's the glue between multiple systems.
My name is Sergey Semyonov. I'm a development engineer here at DTU Wind. I joined 7 years ago. The ARAMIS system is really easy to use. You just need to show the calibration object to a system and then obtain the lenses distortion and the camera positions, and you're ready to go. The software suite is quite handy for measurements post-processing, comparisons with CAD data and finite element simulation results. It also has quite a powerful scripting engine for simplifying routine tasks. In daily work, ARAMIS will be quite often used as a full field displacement measurements tool, where the movement is so complex that you won't be able to use standard sensors like LVDTs or fire sensors. We also quite often use it as a strain measurement system, as well as point tracking. A major challenge with strain gauge measurements is their point-wise nature. The ARAMIS system will give you a full freedom of obtaining full field measurements. It's really handy in cases where the failure region is not well known in advance, so the placement of the strain gauge will be a challenge. Quite often ARAMIS will be used as a validation tool for our finite element models if we would like to capture failure modes and compare those with the finite element simulations. It is also a nice tool to do a point tracking and use it as a crack tip opening displacement sensor, a virtual one. We also quite often use it for blade property extraction when we need to track the cross sections of the blade. From manufacturing perspective, the blades and molds they made out of is quite complex shape structures, so you need to control tight tolerances for those. As an example, we use status scans to check those deviations and see how as-built geometry affects the load carrying capacity of the blade. The point tracking option is really useful for full field measurements as well. So you can capture whatever markers location and afterwards introduce virtual sensors and process your data sets as you like. Quite often we use it as a virtual crack opening sensors and track the crack tip propagation. We successfully adopted the technique where tri-top is used to stitch several Aramis measurement volumes. This allows us to measure 360 degrees around the cross-section, and the movement of such a cross-section could be quite complex, and displacements could be more than 10 meters.
ZEISS equipment and software help us to measure the difference between the models that we are working with and the actual test of the same structures. So in that way, we can improve our models significantly. For the future, we will need measuring systems that not just work in the lab, but we will also need to understand how real structures out in reality works. For instance, a full wind turbine out on sea. We need measuring systems that can determine how the structure behaves, how it deflects, but also when damage comes to these structures, start, initiate and grow, we need to measure that. And I think camera-based non-contact solutions employed on a drone can be one of the solutions to have these kind of measuring systems. So that's some vision I have for the future, that the industry like ZEISS will develop these kind of systems.